In this lecture, we will discuss about the CE amplifier with the resistance at the emitter. So this is my common emitter amplifier. Of course, we don't have a resistance here. So what basically we will do is that we will add a resistance here and see the advantages of it. A resistance Re is added at the emitter. Okay, so we will see the different advantages of this one. Okay, why we actually go for adding this Re. Okay, so before understanding the advantage, let's try to do the DC operating point analysis. Let's try to find out the IB and IC of this one, and from the equation it will be very clear the advantage of this circuit. So to proceed with the DC operating analysis, we need to do the same thing. So we need to find the Thevenin's equivalent model of this one, and then we can throw the same thing. So same thing of this one. So this part is same as this one, and we will be adding a Thevenin's equivalent resistance, the RTH and the VTH. So this is how it gets converted, okay, for DC operating point analysis. And as we know that the my VTH is given by same, right? In this case, it is VDD into RB2 by RB1 plus RB2. The same thing that we did before for the conventional, common emitter amplifier, and RB1 RTH is RB1 parallel RB2. Okay, so this is of course my VTH, and we know that through this there is a current IB flowing inside the base IB, and a current IC is flowing, which is beta times IB, and a current IE will be flowing, okay, through this resistance Re. And of course we know by the KCL that this and this will get sum up to give me IE. Okay, so this IE is basically IB plus C. Okay, so now let's write the KVL in this loop. So if I write the KVL in this loop, what I'll get here is that VTH minus IB into RTH, and we of course we have the BBE drop, so the on voltage of this PN junction or the transistor, which is 0.7, and I have my minus IE into RE is equal to 0. Okay, so now as we know that this IE we can write as IB plus IC. Okay, so implies VTH minus IB into RTH minus, this is 0.7 we know, and this I can write as IB plus IC into RE is equal to 0, and of course IC is beta times IB, so I can write VTH minus IB into RTH minus 0.7 minus IB, I'll take IB as common, so 1 plus beta into RE is equal to 0. So finally I will get, therefore my IB, if I try to estimate my IB, I will get something like this: VTH minus 0.7, so IB common, so it will come this side, so this is RTH plus 1 plus beta into RE. Okay, so now if I try to calculate the IC, so what will be my IC? Therefore my IC will be equal to beta times into this whole thing, beta times IB, which is beta times VTH minus 0.7 RTH plus 1 plus beta into RE. Okay, so we are seeing this term, so now we are seeing this term RTH plus 1 plus beta into RE. So now suppose if we consider a case when this beta times RE is much large, right? So generally we know that beta can be as good as high as 300, right? And RE, even if we consider it to be maybe just 1 kilo ohms, correct? Then the whole term, the product, right, is almost 300 kilo ohms, right? This is around 300 kilo ohms, okay? And maybe if you consider this RTH, maybe just 10 kilo ohms, 20 kilo ohms, right? Correct. So this whole term become much smaller than this, okay? So I can approximate, if this whole term is much smaller than this, then what can I can approximate is, I can approximate with only this one because this is very small, okay? And of course here also the 1 plus beta, because beta is 300, so 1 plus beta can be approximated to only beta, okay? So if my, let's just give some value, so I can write RTH maybe 10 kilo. This is just a particular case, okay? Case 1, okay? So if my RTH is much smaller than beta into RE, or 1 plus beta into RE, then my IC becomes almost beta into, this will be beta into RE by VTH minus 0.7, okay? So if you see here, the beta gets cancelled, okay? So what it means is that my IC is independent of beta, okay? Because there is no term for IC, okay? And because the IC is has a factor on the gain, so we can say that the gain is also becomes independent of beta. So this we will see more in the small signal analysis, okay? So this is a very important conclusion, that the DC operating point, the IC, is not dependent on beta. So but however, if RTH is not very small, like instead of 10 kilo ohms it may be like 100 kilo ohms, but then also still the dependency of the IC on beta reduces, okay? So of course this is not equal to, this is, I should say that, approximate, okay? So point is, if RTH is comparable to beta into RE, then also, okay, the dependency of IC on beta reduces compared to C amplifier with RE is equal to 0. So we have before we have studied that there was no RE, right, when we studied the C amplifier, but introduction of this RE reduces the dependency of IC on the beta, okay? So if we select this RTH to be small enough compared to beta into RE, then the dependency is really negligible. Whereas even if you take it large, right, even if 50-60, still the dependency reduces because this factor has come in the denominator, okay? Okay, so this is what we have seen. Moreover, we will see that when we will solve the numerical, that when there is no RE, the sensitivity of the IC, right, the change of the IC with a change in this resistive divider resistance is very high, right? If there is a small change by 5%, 10%, you will see that the IC changes vary in a huge amount because the beta is being high. Whereas with the inclusion of RE, we will see that the variation of the IC with a change of 5%, 10% of this resistance becomes much smaller. So one may ask, why should I make IC less dependent on beta, or is independent of beta? Why we should try to make? The reason is very simple. Whenever we are designing an amplifier, the beta may get changed, right? Beta may get changed, but I don't want to change my amplification. For example, if I'm using an audio amplifier, if I'm using it for a long time, the device may get heated because of the current flowing through the transistor. Because we know that whenever the current flows, there is heating because of the I square R, right? So now with the heat, the beta can get changed. Beta can get changed. That means my DC operating point can get changed, right? So I don't want my DC operating point to get changed with change in temperature. So with this, we can make the operating point stable. And once we make the operating point stable, we will see that the gain also doesn't change, right? Gain always remains constant. Okay, so this is what we will see next. So now let's try to do the small signal analysis of this circuit and try to find out what is the gain. Okay, so this is the small signal model of the CE amplifier when there is no RE resistance, but now we have to introduce the RE resistance here. Okay, now let's try to calculate the gain. Okay, so I have my IC current here, and of course there will be a current that is flowing, the small signal current, which is equal to IB plus IC again. So let's write down different equations. So we know that in this case also the V out will be equal to minus IC into RC, as we have written before. Okay, so now if we try to write the KVL in this loop, okay, if I try to KVL in this loop, of course the B in is directly appearing here. Okay, B in is appearing here. So basically what I'll have here is V in minus small IB into R pi minus IE, which is basically IB plus IC into RE is equal to 0. Or basically what I'll get here is I can find out IB here. Okay, so what I'll get here, my IB will be equal to, this is basically beta times IB, so IB will come out, right? So then what I'll get here is IB will be equal to B in by R pi plus 1 plus beta into RE. Okay, so this is what I'll get, and here what I can write is implies V out is equal to, again this IC equal to beta times IB is still valid, so beta times IB into RC. So let's call it as equation number 1. So implies my V out will be equal to minus beta. If I substitute this IB here, what I'll get, beta RC into IB is this one, which is V in by R pi plus 1 plus beta into RE. Okay, so therefore my gain, which is V out by V in, is equal to minus beta into RC R pi plus 1 plus beta into RE. Okay, so this is the gain of this amplifier. Okay, so now again let's try to analyze this equation. So any equation that we write, we should be have some conclusion, right? We should be having some conclusion of any equation that we write. Okay, so now if we analyze this expression, suppose if my, we know that r pi is given by pt by ib, okay, which is vt, we know that it is 26 millivolt. And suppose if we consider ib maybe 10 micro ampere, right? Then my r pi will be equal to 2.6 kilo ohms. Okay, so this r pi is in the order of few kilo ohms, but as we have seen, like, and let's make it maybe as high as maybe 5 kilo ohms. Okay, not more than that. And this one, as we have seen, that if I consider this re to be 1 kilo ohms and beta to be around maybe as high as 300, so this whole terms becomes 300k. So now here it is very clear that this whole term is much larger than this r pi. Note that this expression r pi plus 1 plus beta into re, we are going to encounter this expression again and again. Okay, so if you see, this whole term can be approximated as 1 plus beta into re, and and of course if this beta is 300, then 1 plus beta also can be approximated as beta only. Okay, so finally what I'll have here is this is approximately equal to minus beta into rc and beta into re when my beta is much greater than 1 and r pi is much lesser than 1 plus beta into re. Okay, so this is just one case. Okay, so this is not, of course, this is not the absolute, this can vary, beta can be higher than 300 or 400, but typically these are the values, or these are the case, and when this condition is satisfied, so I'll get this approximation. And of course I can beta I can cancel, and finally what I'll get here is this is approximately equal to minus rc by re. Okay, so the gain here is just the ratio of these two resistance rc and re. Okay, so the gain of this amplifier, okay, is going to become very small. It is just going to become the ratio of rc and re. If re I take it as 1 kilo ohms and rc to be maybe 4 or 5 kilo ohms, then the ratio is going to become just 4 or 5. Okay, so the gain is going to become very small. Okay, so yes, we have understood that the IC is stabilized. The IC doesn't change much with the change of the beta, and IC is also less dependent on the variation of RB1 and RB2. But the main disadvantage of this circuit is that the AC gain, the gain of the small signal also is reduced, and finally it is just boiled down to RC by RE. Okay, so the next question is how do we restore the gain? Okay, so to restore the gain, you see, as we have seen that the small signal is almost same, the circuit is almost quite similar to the previous circuit of the CE amplifier where RE was not there, but because of the presence of RE, it makes the whole difference. So the only way is we need to somehow get rid of this RE while doing the small signal analysis. Okay, while doing the small signal analysis, we need to get the RE. The RE has to be there when we are doing the DC analysis, but during the small signal, we need to get it off, right? So just like we use a capacitor to, pass the AC and, block the DC. So here we will also use a capacitor here, and what will happen is if I use the capacitor, all the AC signal will be going directly to the ground. So this node voltage can be approximated to the ground and RE will not appear. So during the small signal analysis, okay, So that's how we can get rid of this Re and restore the gain. Okay. So to restore the gain, we will be using a capacitor here. Okay. We'll be connecting a capacitor at the emitter. So CE. This CE sometimes is called a bypass capacitor because it is helping to bypass this RE for the AC signal. So this is called sometimes as bypass capacitor. So now if you see the small signal, so this RE will not be there. Okay, so RE will get bypassed, and finally in the AC wise here it will be grounded, and my gain will be same as before. So we know that gain of a CE amplifier is IC into RC by VT. Okay, so, and then we can get a very large amount of gain with this expression. But there's a difference, right? Compared to the CE amplifier without this resistance RE, there's a difference. Although the expression of the gain is same, the difference is that the variation of this IC now is going to become very small, because as we have seen that the DC current, the IC, is very much less dependent on beta and also on the variation of the ratio of these two resistance. So that is the difference. So that is the benefit of adding this RE and CE. Okay, so I have got back my gain, but at the same time my DC operating point is very stable. But then one may ask, okay, so is there any disadvantage of this circuit? Yes, there is a disadvantage. Disadvantage is that now if you see the voltage swing, initially the voltage swing, as we have discussed before, it was going from VDD to 0.3, right? VDD to 0.3, if you remember, okay? But now what will happen is this will have some voltage, because a constant current IE is flowing, and this may be settled at some voltage VE. Okay, so now the lowest point here, it will be going instead of 0.3, it will be 0.3 plus VE, because at 0.3 drop is required between the CE, but now this voltage E voltage has already rise to this VE voltage. This may be 1 volt or 2 volt depending upon what is my RE, right? So that's why I cannot make this RE very large. Okay, if I make this RE very large, of course my IC will become very stable, because beta times RE is going to become very, very large. But at the same time, this node voltage is going to become high, so my swing will get restricted. Okay, so to make sure that swing is not much restricted, I cannot select a very large value of RE. So this limits, or this may considers the higher limit of the RE. Okay, so it will be 0.3 plus I into RE, or this is the VE, right? Okay, so the initially it was VDD to 0.3, but now it will be reduced, right? The lower limit will be increasing by IE into RE. So instead of reduced to, so reduced by, I should say, IE into RE. Okay. To appreciate whatever we have learned, let's consider an example. So first, let us consider a CE amplifier without RE. Okay, maybe let's call it as case number 1. Okay, and then we'll do the same estimation considering the RE resistance. Okay, let's give some values to this resistance, and of course beta to that resistor. Let's call this RB1 maybe 125 kilo ohms, RB2 be 10 kilo ohms, RC may be around 3 kilo ohms, and beta to be 300. Okay. So here what we'll get RTH, therefore RTH, we know that it is RB1 parallel RB2. So if we take this parallel of this one, we'll get a value of 9.26 kilo ohms. Okay. And my VTH, which is given by RB2 into VDD by RB1 plus RB2. Let's consider VDD to be 10 volt. So considering VDD to be 10 volt, this value is 0.74. So therefore my IB, I'm directly writing the equations because we have already discussed these things multiple times. So I'm not even showing the diagram. But of course in exam you're supposed to write everything in details. So IB is VTH minus 0.7 by RTH. So this comes out to be around 4.3 microampere. I suggest you can do the calculation yourself. So this will give you confidence. So therefore my IC, which is equal to beta times IB, will be equal to 300 into this one. It is coming out to be around approximately 1.3 milliampere. Okay. And of course my gain, which is minus ICRC by BT, is coming to be 150. If I substitute all the values, RC is 3 kilo ohms and VT is 26 millivolts. Okay, so now it is clear here that with the change in the beta, my IB doesn't change, right? And my beta IB is dependent only on RB1 and RB2. Okay, so maybe we want to estimate what is the change in the gain and the IC with a change in beta. Okay, so maybe let's consider maybe 10% change. So with 10% change in beta, okay, with 10% change in beta, it is very clear that my IC will change by 10%. So IC changes by 10%. Okay, and if IC changes by 10%, my AB also changes by 10%. Okay. Okay, so of course this we know that it can be directly estimated from this formula. Then the question is, why have we done all the calculations? Okay, I have done this calculation to show the change in IC and the gain with maybe change in RB. Okay, RB1. So now okay, with change in RB1 by maybe let's call maybe my minus 5%. Okay, so RB1 has reduced by 5%. So let's see what happens. Okay, so therefore my new RB1 will be equal to so RB1 was 125 kilo ohms. So 5% of that is 6.25 kilo ohms. It's reduced. So now it is 118.75 kilo ohms. Okay. So with this, my new RTH becomes 9.22 kilo ohms. And my new VTH becomes, I'm directly estimating it, you can also try yourself, okay, 0.77 volt. I suggested please calculate yourself. So we need to do all the recalculation of this one because we know that IB is dependent on RB1 and of course eventually IC is dependent on it and also the gain. Okay, so now therefore my IB will be equal to VTH minus 0.7 by RTH. Okay, again the standard formula. So with this, my IB becomes, if I substitute all this value, the new values, it becomes 8.3 microampere. Okay, so therefore my IC now it becomes, 300 into IB is equal to 2.4 milliampere. So you can see here there is a good amount of change in the IC. Okay, so change in the IC, or the percentage of the change in the IC, delta IC by IC, I can calculate it as 2.4 minus, previously it was 1.3 milliampere, 1.3, maybe let's estimate in percentage, so it comes out to be 84%. So you can see here that with just a 5% change in RB1, my IC changed by 84%. So even the gain also will change by same amount, 84%, because we know that the gain is just directly dependent on the IC, right? RC and VT are constant. So if my IC is changing by some amount, some percentage, X percentage, my gain also will change by that same quantity. Okay, so we can see here that with a some percentage change in the beta, my IC changes proportionately, because IC and gain is directly proportional to beta, but there is a huge amount of change. There's a very much sensitive to the change in the RB1 or RB2. Okay, so this is what we see in this topology where there is no RE resistance. So now let's now try to estimate case 2 with including RE. Okay, this is my case 2. So of course here there will be a slight variation in the values. This is my RE resistance, and let it be 1 kilo ohm, and this one will change a bit. This will be 40 kilo ohms. Okay, I've taken this value of the resistance such that my IC is almost same as the previous one, so that the gain is similar. Of course we need a capacitance here, the bypass capacitance, so that the gain is same, the expression of the gain is same. Okay, so let's start the calculation. So my RTH in this case will basically 40 kilo ohms parallel 10 kilo ohms. So it is 40 kilo ohms parallel 10 kilo ohms. So this is coming out to be 8 kilo ohms. My VTH is coming out to be, this is RV2 into VDD by RV1 plus RV2. So this is coming to be 2 volt. Okay, so now therefore my IB, again I'm here also I'm writing the expression directly. We have already discussed previously, so I'm not again discussing here. So VTH minus 0.7 by RTH plus 1 plus beta into RE. So if I substitute all the values, it comes out to be something like this. This is 2 minus 0.7, this is 8 kilo ohms, plus this is 301 because my beta is 300, and of course this is 1 kilo ohm. Okay, so the value comes out to be approximately 4.2 microampere. Okay, so this is my IB. Okay, so therefore my IC is beta times IB, and if I multiply 300 with 4.2 microampere, I will get a value of around 1.262 around. Okay, the reason why I'm taking 2 will be clear later on. Okay, so it is milliampere. Okay, and of course therefore my gain is, in this case also it is same, minus ICRC by VT. So if I estimate this one, it comes out to be around minus 145.6. Okay, so this gain is quite close to the previous gain of 150. Okay, so here what we are focusing is not the absolute value, but how much is the variation. Okay, so now let's try to estimate with a 10% change in beta. Maybe let's consider with 10% increase in beta. Okay, so with 10% increase in beta. Okay, so therefore my new beta will be 300 plus 10% of 300 is 30, so it is 330. Okay, now therefore my IB, so my IB is going to change now, because we know that if you see here the expression of the IB, it has RTH, BTH and 1 plus beta into RE. Of course, VTH and RTH will not change, we change in beta. Okay, so it is basically my VTH minus 0.7 RTH plus beta plus 1 into RE. Okay, let's substitute with the new values. So what I'll get here is, it is 2 minus 0.7, my RTH is 8 kilo ohms, plus now beta plus 1, it will be 331. So this will give me an IB of 3.83 microampere. Okay, therefore my new IC is going to become beta times IB, which is the new beta is 330 into 3.83 microampere. So this comes out to be around 1.265, okay, milliampere. So we can see here the change is really small. So previously it was 1.262 and 1.265. Of course, depending upon how much precision that you are taking, you'll see that the results are, the precision depending on that, but it's really less than 1%. Okay, so therefore delta IC by IC, in this case it will be around 1.265 minus 1.262 by 1.262, so it comes out to be around 0.3%. Okay, so depending upon what value, how you are calculating, this value may vary, but the point here is that it is less than 1%. Okay, so in the previous discussion, when we were not having RE, you see the change in IC is directly proportional to change in beta. But we can see here now that the change in the IC and the gain is reduced even to lesser than 1%. Okay, and of course the same as change in AV is also same, which is 0.3%. Okay, so now let's consider we change in the RB1 by, again, minus 5%. So my new RB1 will be, RB1 is equal to, it was initially 40 kilo ohms, now minus 5% of 40 kilo ohm is 2 kilo ohm, so it is 38 kilo ohms. Okay, my new RTH will be, of course, RB1 parallel RB2, it is coming out to be 7.91 kilo ohms. Please try to estimate yourself. Okay, this will give confidence in solving this kind of problems. So VTH will be, the new VTH is around 2.08 volt. Okay, again I'm writing the new equation of the IB. So my IB will be, again, VTH, new VTH minus 0.7 by new RTH, and of course in this case beta plus 1 is there, into RE. So if I substitute all this value, my new IB will come out to be 4.47 microampere. Okay, therefore my new IC will be beta times IB is equal to 1.34 milliampere. Okay, so now therefore my change in the IC, delta IC by IC will become, so it was 1.34 and previously it was 1.26. Okay, I'm dropping the 2. 1.26 of course into 100 will give me a percentage, so it is around 6.6%. Okay, and of course my delta AV by AV also will change by 6.6%. Okay, so previously if you see, if you are not having RE, the change was quite huge, right? It was, if you remember, it is 84%, right? 84% was the change, but now the change is only 6%, 6 or 7%, 6.6%. So there's a huge amount of reduction in the change in the gain in the IC with change in RB1. So it makes the circuit more robust or less sensitive to the variation of RB1 and RB2. So then design becomes simpler, otherwise it becomes very sensitive. If you just change this one a little bit, then you can see there's a huge amount of fluctuation in IC. Okay, we want the whole circuit to be less sensitive to RB1. The reason is so that if we have designed the circuit for some variable and we may not get precisely that value, right? Because generally what happens, if I say that RB1 is 40 kilo ohms, but when I'll be taking the resistance from the manufacturer, they will always say that there is some tolerance, right? There will be like I may give you 40 kilo ohms, but there may be some plus minus 5% error, right? So if that kind of things comes, then what happens is this circuit becomes more robust. Okay, whereas we have seen that with even with a plus minus 5% in the previous circuit, there's a huge amount of sense. So you have designed something, but by the time you start implementing the circuit, because there is an error in the value of the resistance, what happens is you don't get the accurate value of the IC. Okay, so with this we will conclude this discussion on the common emitter circuit with with source resistance. Here I just want to give a small correction in the discussion, which I have just corrected now, that I was including RS while doing the discussion in the diagram, but in the small signal the RS was omitted. So just do this correction that RS will not be there. Okay, consider RS to be 0 in this circuit. Okay, for simplicity. Of course, if you include RS, then what happened? There will be a voltage division that is happening here. So that also can be done. Okay, so this kind of problem we'll consider when we will solve some practice problem. But for here, you can just omit the RS or make RS 0, to solve these problems. Okay, with this we will end this discussion. Thank you.